Hello, chemists. This is Miss Placino, and you are watching Screencast 10.1 on types of mixtures. In today's lesson, we're going to cover the different types of mixtures that exist, and we're also going to talk about how you can differentiate between them. We're going to start off with solutions, and the majority of this unit is really going to focus on solutions. So let's get some definitions down first. A solution is a homogeneous mixture composed of two or more substances. All the solutions that we're going to look at right now in chemistry are really just going to be composed of only two substances. You can definitely have ones that are more complicated, but we're going to try to keep things fairly simple for the time being. So a good example of something that's going to form a solution is if you take sugar and dissolve it in water or salt and dissolve it in water. Remember, when we're talking about a homogeneous mixture, we're talking about something that is the same throughout. Usually these solutions are going to be made up of very small particles. Often we're talking about something on the order of atoms or ions or small molecules. If they're too much bigger than that, they're not going to be able to stay suspended in the solution, and they're going to settle out. And then it's not going to be homogeneous, and therefore it cannot be a solution. And just what we talked about, solution does not separate on standing. So it should stay homogeneous pretty much indefinitely. Continuing on with some definitions. We're talking about solutions. The two pieces that make up a solution are the solute and the solvent. The solute is the material that is being dissolved. It can be really any phase of matter, solid, liquids, or gases, but at this point in time in chemistry, more often than not, our solute is going to be solid. The solvent is the material that is doing the dissolving. Again, it can be a solid, a liquid, or a gas. There are examples of solutions that are two solids mixed together, examples of two gases mixed together, but for our purposes in this class, we're usually going to be looking at a liquid, more often than not, water being our solvent. And we always take the solute and dissolve it in the solvent. So those of you who drink coffee or tea in the morning, you're making a solution as you add your sugar to your beverage. One of the things that we're going to have to do this semester, or I should say this unit, is predict solubility. Predict if two substances will in fact dissolve in one another and form that homogeneous solution. If they are able to do that, we'd say that the substances are soluble in one another, or that the salt is soluble in water, and that's just saying it's able to dissolve in the solvent. Insoluble, as you might imagine, is the opposite. It is unable to dissolve in the solvent. So something like lead iodide, PbI2, that's that yellow precipitate that forms in different chemical reactions that we've run in the previous semester. That is an insoluble compound. It does not dissolve in water. You cannot form a homogeneous mixture. In order to predict solubility, if we're not talking about ionic compounds, we have a phrase in chemistry that we say, it's likes dissolve likes. And what we're talking about when we say likes is polarity. And I know for a lot of new chemists, polarity is something that can be really kind of challenging. It was tough the first semester when we were talking about it in bonding. It's still challenging now, so I want to take a couple minutes to review. But our application for with polarity, what we're doing today is if you're going to have two substances dissolve into one another and form a solution, they have to have the same polarity. So let's quickly review. All right, hopefully you recognize this as the water molecule. Is this a polar or non-polar molecule? Hopefully you're thinking that this is polar. Whether you can explain why it is or you've just memorized that water is polar, we'll take it. So just to review, polar means that there is an unequal distribution of charge. What we mean is that one side of the molecule is going to have a negative or a slightly negative charge, and the other side of the molecule is going to have a slightly positive charge. This is because the electrons are not shared equally between atoms. So if you were to go into your reference table and look up electronegativity, you'd see that oxygen is very electronegative. I think it's like 3.5. Hydrogen, not so much. It's only 2.1. So they're going to have an uneven sharing of electrons. Essentially, oxygen is going to pull them towards itself, making oxygen, oops, let's put that back, slightly negative. We use the lowercase delta, kind of looks like a music note. And if the electrons are being pulled towards oxygen, that means the hydrogen doesn't really have that much possession of them. So the hydrogen side of the molecule is going to be slightly positive. Oftentimes, a polar molecule, especially at this level of chemistry, is going to have unshared pairs of electrons on the central atom. So these dots that are sitting on top of oxygen, those represent electrons that are not involved in bonding. They belong solely to oxygen. And that's oftentimes a pretty good indication that you are looking at a polar molecule. And the other way we can look at it is through symmetry. If you try to draw lines of symmetry on a water molecule, you really only have that one line of symmetry. Now, this is why it's important that you draw your molecules correctly. This is not a highly symmetrical molecule. It's got only one plane of symmetry. Other molecules might have no planes of symmetry. That's usually a pretty good sign that you are looking at a polar molecule. All right, using your amazing powers of deductive logic, you could probably conclude that a molecule like CH4, methane, is nonpolar. Nonpolar means that we have an equal or even distribution of charge. In other words, if you were to look up the electronegativities of carbon and hydrogen, you'd see that there's a small difference at 0.4. So the carbon actually is going to pull the electrons towards itself a little bit. But if carbon is pulling a little bit away from this hydrogen and a little bit of the electron density away from that hydrogen, so on and so forth, everything kind of cancels itself out. So this guy's a little bit positive, a little bit positive, a little bit positive, a little bit positive, a little bit negative. And if we took the average location of the slightly positive charges, they're going to end up right back on the carbon. So they kind of cancel each other out. We say that this is an even distribution of charge, and therefore a polar molecule. If you're thinking, oh gosh, that's a lot of work to do for every molecule, here's a couple of shortcuts you can use. Oops. Usually nonpolar molecules, your central atom has no unshared pairs of electrons. So in this case, we don't see any of those big electron pairs like we saw on oxygen in the water molecule. Carbon doesn't have any of that. All of its electrons are involved in bonding. And our nonpolar molecules tend to be highly symmetrical. So I can draw a line right down the center, around the halfway mark. I could fold it. I can go on the diagonals. See 4 planes of symmetry. So this is a highly symmetrical molecule, and therefore it's going to be nonpolar. And that's really the gist of it. There are a couple of practice problems in your workbook. I really suggest trying them out and making sure that you feel comfortable differentiating between polar and nonpolar molecules. This unit really relies heavily on a lot of first semester stuff, and we're going to see that as we continue. Okay, getting back to classifying different mixtures, we have suspensions. A good example of a suspension, is a snow globe. You probably know from experience that if you take the snow globe and shake it up, you can get the snow to kind of disperse all over the place. And then if you leave it and you don't shake it, the snow is going to fall and essentially come out of the solution and settle on the bottom. That's exactly what a suspension is. Those particles of solute are so large that they cannot stay kind of floating, for lack of a better way to describe it, in the solvent. They're going to settle out unless you constantly stir or shake or agitate the mixture. So a good example of this is sand and water. And the last type of mixture I want to talk about is a colloidal dispersion, sometimes just called a colloid. You'll hear them called both. Don't be confused. They're exactly the same thing. Colloids are kind of medium-sized particles. The particles are too big to be considered a solution, but they're too small to be a suspension. These are particles that are going to be able to stay distributed homogeneously through the solvent. So the idea or the example of smoke, you've got really tiny particles of solid that are distributed through the air. Something like whipped cream or shaving cream, you have kind of like a liquid medium with a lot of air or carbon dioxide pumped into it. Same idea. Eventually that's going to settle out and kind of go flat. A lot of your food products tend to be colloidal dispersions or colloids. Mayonnaise and butter are 2 examples of that. So you've got particles, solute particles, I should say, that are too big to be considered a solution, but too small to be considered a suspension. Differentiating between a solution and a colloidal dispersion can be challenging. Luckily, there's a really cool way that you can determine which is which, and that's called the Tyndall Effect. The Tyndall Effect is the scattering of light by small particles. Have you guys ever watched like a movie where people are like trying to steal like jewelry, or they're trying to steal a famous painting? If you have, you might, maybe in the movies you've seen, these expensive pieces of jewelry and famous pieces of art are often being protected by like a laser beam system, where once somebody breaks the beam, the alarm's going to go off notifying the police to come. And sometimes you'll see them pull out this like magic spray can, and they'll spray the area and they'll be able to see where the laser beam is. Now, this isn't just Hollywood magic. This is an example of the Tyndall effect. Something like chalk dust or hairspray is going to create a colloidal dispersion in the air. In this picture, we've got two very similar looking test tubes full of mixtures. The one on the left is a solution. The one on the right is a colloid. As light is shown through both of these mixtures, in the solution you don't see anything, but in the colloid you see a beam of light. That is because the particles in a colloid are large enough so that the light is able to bounce off of them. So we observe the Tyndall effect in a colloid. We do not observe it in a solution. Oops, wrong way. But you can make your own colloids at home. Again, it's as simple as spraying like hairspray or getting chalk dust, those really fine particles into the air, and you'll be able to see the beam of light through it. So that's actually something in Hollywood that works in real life. The last two things that I'd like to talk about are electrolytic and non-electrolytic solutions. I think this came up during first semester, but just to review, an electrolyte is probably a word that you've heard before. If you drink Powerade or Gatorade or any of those sports drinks, they're telling you that when you sweat, you lose more than just water. And you've probably noticed when you taste your own sweat, and I don't mean by like licking your arm while you're running, but you lick your lips, it probably tastes salty. Electrolytes is kind of another name for a salt, very, very generally speaking. An electrolytic solution is one that is going to conduct electricity. So there are times when something's going to dissolve in water and turn into a solution that conducts electricity because you have mobile ions in solution. So I think we've seen pictures like this before. If you take something like sodium chloride, an ionic solid, and you dissolve it in water, the water molecules actually come in and rip the crystal lattice apart. Water is polar, so the positive side of the water molecule is going to be attracted to the chloride ion. The negative side of the water molecule is attracted to the sodium ion, and it can kind of pull the crystal lattice apart and get these ions into solutions. Once you've got mobile ions in solution, you can conduct electricity with that solution. Non-electrolyte is exactly what you probably think it is. This is a substance that dissolves in water and forms a solution that does not conduct electricity. Oftentimes we're talking about molecular substances, things that are covalently bonded together. So you've got sugar, back to biology, C6H12O6. Sugar will dissolve in water, but the covalent bonds between the carbons, the hydrogens, and oxygens present in that molecule do not break apart. So while something like sodium chloride is going to break apart or dissociate in water, something like sugar essentially just gets wet. It's called solvated. It'll end up with water molecules around it. The sugar molecules will be free to float around in solution, but you will not conduct electricity. All right, just to wrap up, here's a question for you. You've got 3 beakers containing aqueous solutions of NH4Br, ammonium bromide, HCl, hydrogen chloride, hydrochloric acid when it's dissolved in water, and C6H12O6, glucose. Is it possible to differentiate between the solutions? If so, how? And tasting them is not allowed. You never want to drink things in the chem lab. That does not usually end up working out in your favor. So take a couple minutes, see if you can figure that out, and I hope this lesson was helpful, and I'll talk to you soon.